speaker is Ekaterina Babintseva, who works as a historian of science and technology at the College of Liberal Arts at Purdue University. She has two book projects. One examines mid-century artificial intelligence by attending to the history of Soviet and American pedagogical computing. And the second project is concerned with the history of machine translation during the Civil War. So today, Ekaterina will give us the talk on freedom and control, making up minds and machines in the Soviet Union and the US.
Thank you very much, Nicola, for the introduction. It's been such a pleasure to be a part of the History of Modern Mathematics program. Many thanks to the organizers and to the Isaac Newton Institute. And I'm especially excited about the opportunity to speak at the final workshop about my research in the history of computing, especially in relation to the history of mathematics. But before I talk about mathematics, I'd like to tell you about a monograph in the Soviet history, a recent one. So the title of the monograph is "To the Success of Our Hopeless Cause." And it was written by the historian Benjamin Nathans. The book is not about computing or data. It's actually about Soviet dissidents. Even though there is one chapter about a Soviet dissident/mathematician who sought to develop an ideal, transparent human language that would conform with the principles of mathematical logic. So that chapter is, I think, really relevant to the history of Soviet mathematics. But it wasn't just that one particular chapter that drew me to this book. It's the central question of this monograph that I found to be particularly relatable as a historian of computing. And that question is, how can liberty be created in an unfree system? In Ben Nathan's book, the unfree system is the Soviet Union. But I'd like to take up his framework and apply it to thinking not only about a socio-political system, but a technological system as well, the computer. Historically, the computer has been a paradigmatic control and command technology. It originated as a bureaucratic and military machine. And here you can see some of the first electronic computers used in military and commercial contexts. MIT's Whirlwind, which provided the foundation for the US air defense system in the early Cold War. And the other one is UNIVAC 1, used by the US government to process census data.
We don't see anything.
Oh, I'm sorry, yeah. Thank you, yes. So, yeah, the Whirlwind computer used in the US air defense system and the UNIVAC 1 used for the processing of the census data. Okay, so these two were the instruments of military and state control. But at the same time, pretty early in the history of the digital computer, we see aspirations to make this technology into something more than mere tools of control. Take, for example, early developments in artificial intelligence, such as the logic theory machine by Herbert Simon and Alden Newell, that used heuristic algorithms to do proofs from Russell and Whitehead's Principia Mathematica. This program ran on the Joniac computer. This is one of the classic examples of mid-century efforts to make the computer do something that wasn't fully pre-programmed by humans. In other words, I think of the logic theory machine as an effort to make the computer exhibit some freedom in making decisions. And if we step away from the history of artificial intelligence and automation of proofs, we can also see the aspirations to use computers as instruments of counterculture movement, rather than as tools of military and state control. And one of such efforts was the electronic Whole Earth Catalog, a peer-to-peer information system. So what I'm get into is that historically computing has oscillated between the notions of control and freedom. And this tension between control and freedom is especially apparent in the history of Soviet and American pedagogical computing in the 1960s and the 1970s, which is the subject of my talk today. Soviet and American pedagogical computers were designed to fully replace teachers in secondary and university education. On this slide, you can see key examples of such computers. One, an American computer called Plato, built at the University of Illinois, and the Soviet computer Tutor, built at the Moscow Power Energy Institute. These computers were created to cultivate a special kind of workforce. They trained efficient learners and fast problem solvers who would advance the techno-scientific progress on both sides of the Iron Curtain. Because the purpose of these pedagogical computers was to hone students' cognitive skills, I treat this technology as one of the first behavioral digital technologies designed to shape how we think and learn. In the 21st century, digital technologies are routinely deployed in shaping individual behavior and public opinion. Rebecca Lemov and Shoshana Zuboff have written on this subject quite extensively. But the pedagogical computers I study were trained without any evil plan in mind. They were not designed to brainwash or exploit. Perhaps at odds with our historical intuitions, the developers of pedagogical computers were committed to the ideals of freedom. They wanted to cultivate free thinkers with their technology. Today, I'm going to explore how the ideals of freedom shaped these pedagogical computer projects. I argue that the authors of these projects faced serious technological and theoretical challenges when they attempted to encode the ideals of freedom into these technologies. The structure of my talk today is the following. First, I will discuss the University of Illinois Plato computer. Plato is an acronym standing for Programmed Logic for Automated Teaching Operations. And in particular, I will focus on two Plato projects that were driven by the ideals of freedom: a computer-based mathematics lesson called Proof, and a System for Instructional Response Analysis, or SIRA. Both of these Plato projects were developed by psychologist Jack Easley, who eventually became a critic of pedagogical computing. And I will talk about his criticism in the third part of the US part of this talk. In the USSR, researchers knew about Plato and considered it to be the paragon of a teaching computer. They wanted to purchase 9,000 Plato terminals from the United States, but the deal never happened. Left to their own devices, Soviet researchers had to develop pedagogical computers on their own. So in the second part of this talk, I will discuss the work of Soviet psychologist Lev Landa, who set his mind on developing algorithms of rational thinking for Soviet students. All right, and then I will draw the conclusions and talk about, the future directions of this research. All right, so part one. The Plato computer was developed at the Coordinated Sciences Laboratory at the University of Illinois. In the 1950s, the lab received lavish US government funding to build a digital computer, ELIAC. ELIAC analyzed radar patterns and evaluated atomic blast effects. When the Korean War ended in 1953, the lab had to find a civilian application for ELIAC. In the next 2 years, CSL engineers connected ELIAC to TV screens and keyboards and created a pedagogical system that they hoped would be able to replace human instructors. The system was named Plato. And here you can see the very first version of this computer. The photo that I showed earlier was a more technologically advanced version of Plato. CSL was an engineering institution consisting of mathematicians, physicists, engineers, but also of psychologists and educators. And in fact, CSL cultivated interdisciplinary connections with other research units at the University of Illinois. And one of those units was the University of Illinois Committee on School Mathematics, UICSM, which was directed by Max Berberman. UICSM was formed in 1951 as an effort to reform and improve math curriculum at all levels of education. As the historian of mathematics Christopher Phillips has shown, from 1959 to 1965, the US witnessed the emergence of the so-called new math reform groups, and UICSM was one of them. These groups worked to change the existing mathematical curriculum that they thought placed too much emphasis on students' ability to give the right answers. The new math reform advocates maintained that teaching mathematics as rote memorization was the wrong way to think about mathematics. And more generally, rote memorization came to be linked to an authoritarian style of learning and reasoning, which is incompatible with the values of Western liberal democracy. So Max Berberman advocated for teaching students in a way that would prod them to discover the key principles of mathematics. But Berberman also viewed mathematics as the study of structures and systems, and he believed that learning the rules of logic was an essential element of learning mathematics. So in Berberman's approach, students learned the structures and rules not by rote memorization, but through discovery. Many of the textbooks produced by the advocates of the new math reform relied on Berberman's vision of mathematics as the study of general abstract systems, and they emphasized deductive reasoning. All right, so one of the affiliates of the UICSM was psychologist Jack Easley. He created a Plato-based course on mathematical proofs in elementary algebra. That work was funded by the US Army, US Navy, the Air Force, and the NSF. And it was one of the most prominent collaborative projects between CSL and Max Berberman's Committee on School Mathematics. The collaboration was also possible thanks to the additional funding from the Advanced Research Projects Agency, or ARPA. ARPA was a landmark American Cold War institution which in the 1960s and the 1970s created a large-scale computer network, a prototype of the contemporary internet for American military. ARPA funding allowed behavioral scientists like Jack Easley to use Plato in their research on teaching, education, and man-machine interaction. And at the same time, the collaboration provided CSL engineers with insights into further improvement of the Plato computer system. Jack Easley's course on mathematical problem solving was called Proof. The first report about the program came out in 1964. The program was coded in Iliac language and ran on Plato 2 terminal. The photo is featured at the top of the slide, and the Plato terminal was connected to Control Data 1604 computer, which is shown here. Okay, so here's what this program essentially did. It presented students with a theorem. A student then had to make a chain of derivations, each of which was checked by the program. The computer did not have a pre-stored set of correct solutions. Instead, it was equipped with the rules of mathematical logic. The Plato system had to perform calculations, checking each line of a student's proof to inform the student whether he or she was following or violating the principles of logic. So the image that you see was taken from Easley's report, but it essentially shows what students saw on the screen at the start of the exercise. So as Easley explained, Plato thus simulates a teacher who watches students at work and tells them whenever they make an effort, but doesn't tell them what they should have written. Okay, so let's take a look at what was it like to do mathematical proofs working with Plato. And I'd like each of you to just take 10 seconds and prove this theorem just for yourself. I mean, 10 seconds should be enough, right? Okay. Okay, now that you figured out how to prove that the left is equal to the right, let me show you what the students had to do to prove that the left was equal to the right. Okay, so first the students replaced x by a and y by b. All right, well, and by the way, what you see on the right is, this is how I wrote the same thing that students were writing, because I just found the usage of the parentheses to be extremely confusing. So just for the sake of clarity, I guess this is written in a more accessible form, at least to me. All right, so, and then the students represented a minus as a multiplied by a by minus 1, and the next line is this transformation. Okay, so the point is that I think it looks extremely bizarre, right? The way how the students had to approach this kind of proof. And I'm sure that when I asked you to take a couple of seconds to do this proof, none of you have written this, have written or just even thought about this. But that was the point of the program. It taught the rules and structures and deductive logic emphasized by Berberman. Easley's introduction to this report on this program is extremely interesting. For example, he acknowledges that the experience of working with this system is different than, for example, writing proofs manually. And it's especially interesting that I'm speaking about this computer-mediated way of writing proofs at the Isaac Newton Institute, where people constantly write on blackboards. And I'm also thinking of Michael Barani's work on the materiality of proof making, especially the importance of the chalk and blackboards in the communication of mathematical ideas. So this is a very different medium of for the student to communicate their ideas to the student. Okay, so if students were not writing proofs manually, then how did they communicate their solutions to the computer? And here is the device that they used. It was called the proof key set, and it was connected to the Plato terminal. Each button of the key set was assigned a particular numeral, a function or a variable, and you can also see buttons assigned to different kinds of operations. For example, erase the screen, which I guess is analogous to erase everything from the blackboard, or scratch a line. Okay, so Easley recognized how rigid this system was, but he defended its rigidity. He writes that for this automated teaching system, it is impossible to give the students the freedom to write the proofs in whatever way they want. Students also need to justify each step with a particular axiom or theorem. Easley also acknowledges that mathematicians rarely write proofs in linear chains, and in fact, the recent work in automated proofs specifically sought to emulate the mental shortcuts performed by mathematicians. And here he's particularly referring to Simon and Newell's logic theory machine, which I mentioned in the opening of this talk. The logic theory machine did proofs from Whitehead and Russell, Springkeeper, and Mathematica, and Simon and Newell specifically sought to endow the program with the human-like ability for non-deductive reasoning. So here is an interesting tension. In the realm of automated theorem proving, researchers sought to emulate how mathematicians do proofs. But in the realm of the automated teaching of theorem proving, students pretty much had to learn how to think deductively. And I think this passage from Easley's report is particularly striking. The Plato proof system should make clear to them, meaning students, a mechanical procedure by which they can certify that a line of proof follows from its premises. This procedure is the student's mental analog of the actual procedure which would be used by the computer to check the validity of that same line. So essentially, the program taught students to do proofs like a mid-century computer. And that kind of rule-bound way of doing proofs was in line with the UICMS project. So to conclude my discussion about the proof program, Max Berberman and UICSM saw the teaching of deductive logical reasoning as the antidote to authoritarian, unfree modes of thinking. But when Berberman's vision of math pedagogy was implemented with the Plato computer, it was transformed into an even more regimented process, and that regimentation was amplified by the material restraints of Plato. So now I would like to move to the second study from my work on Plato computer, and I'm going to talk about the system for instructional response analysis. I mentioned that even though students had to do proofs in this routinized step-by-step way, they had to discover rather than memorize these procedures. So how do you organize the learning material in such a way that it would prod the students to discover in the most optimal ways? Easley, just like many present-day developers of computer technologies, believed that collecting student data would help in perfecting Plato courses and finding the best ways to design courses that would facilitate the discovery process. Easley's project, Syra, served specifically the task of data collection. Here is an example of data collected from one student working on the Plato computer. It documents the time spent on each chunk of information, when a student requested a help, specifically when the student pressed the help button for additional information to be displayed on the screen, what answers the student provided, and if they were right or wrong. But Easley was particularly interested in a very specific kind of data, which was heart rate data. And this report that you see here was created by one of his research associates, Avner. So why would Easley be interested in measuring students' heart rates when they do mathematical proofs? So Easley and Avner suggested that when a student discovers the principles that they are supposed to discover, their heart rate goes up. And knowing exactly when in the course a student discovers a principle or a concept would aid in a better design of computer-based courses in mathematics. The data that Easley and his colleagues collected was then subjected to statistical analysis. This doctoral student, Kikumi Tatsuoka, was affiliated with CSL and the Department of Psychology at the University of Illinois. She did a lot of work with the student data accumulated by the Plato team. And this particular paper, Tatsuoka used statistical analysis to determine whether students' mistakes were accidental or represented a pattern of a profound misunderstanding of a particular mathematical concept. This analysis of students' response patterns meant to help predict students' future test performance. So essentially, her work was one of the first instances of employing data collected with digital technologies to calculate human subjectivity. Kikumi Tatsuoka is now an emeritus research professor at Columbia University, and according to Google Scholar, one of her research interests is psychometrics. And I think it's fair to assume that her work with Plato, when she was a graduate student, supplied her with the foundation for her work in psychometrics. In the introduction to this talk, I said that I treat these pedagogical computers as behavioral technologies. The Plato project, as I've just shown, was one of the first efforts to employ a data-based approach to engineer human behavior, and in this case, learning. In her account of the Plato computer, historian Joy Rankin has claimed that coordinated sciences laboratory necessitated very different kinds of collaborations and questions than computing labs at MIT and Stanford. And Rankin made this claim based on her study of how Plato terminals at the University of Illinois were connected together, and they kind of presented one of the first computer networks that allowed for communication between Plato users. But the questions and collaborations that I am interested in are those at the intersection of psychology and computing. Media studies scholar Luke Stark uses the term algorithmic psychometrics to describe how online platforms and social media collect information about users to make predictions about their behavior. And I see the origins of algorithmic psychometrics in the work on Plato conducted by Illinois psychologists and educators. Okay, so that was Project Syra, and now I'd like to move to the third example from the US part of this talk, and I would like to discuss how Jack Easley ultimately became disappointed in the Plato project. At the 1979 meeting of the Canadian Mathematics Education Study Group, Easley offered an overview of his career, explaining his collaborations with Max Berbermann's group, with the Plato project, and how eventually he moved away from pedagogical computing, finding it intellectually unsatisfying. Well, first of all, he admits that Syra was pretty useless. Not in this conference presentation, but in a different paper, he says that Syra collected a lot of data that actually didn't help in designing better courses, and he and his researchers were drowning in it. In the early 1970s, Easley and his colleagues came to a realization that the data that they were collecting wasn't really useful. And so what they did, they opted for the so-called offline evaluations. He explained that when teachers observe a student solving arithmetic problems, they could notice the subtle behaviors inaccessible to the computer, such as the hesitation with which a student gives the correct answer. And in that case, a teacher would provide additional problems on the topic so that a student could completely understand the subject. But in contrast, the computer could not register those subtleties of human behavior. So this passage may appear confusing because it actually uses the phrase response data, but what they mean by response data here is information acquired through student observations. As you know, I probably could have stopped my discussion of Easley here, and we could just have a laugh about this kind of naive belief in the power of data and quantification and how he became disappointed in that previous effort. But I won't stop here, and I will continue talking about Easley because his experience with Plato led him to a new theory and philosophy of education. After spending some time developing systems for quantitative data collection and analysis, Easley eventually became an advocate of qualitative, especially ethnographic research. In the 1970s and the 1980s, he conducted hundreds of ethnographic classroom studies. He was particularly interested in how mathematics is taught at elementary, secondary, and high school level. And I would say he made a lot of quite progressive claims in his studies. One of them, for example, was that he was arguing that mathematical success requires confidence, because you need confidence to take intellectual risks. But he was saying that in the US context, that intellectual mathematical confidence comes with a certain class, gender, and race. But today I'm going to focus on Easley's foray into psychology of learning. So here is a paragraph from one of his papers. Even in the most educationally valuable classrooms, there is a significant amount of missed communication that would shock teachers if it were demonstrated to them. That is, as teachers, we always think we understand a good deal more than we really do of what students are thinking. And that misunderstanding, Easley argued, stemmed from a misunderstanding of child cognition. At that time, in the 1970s, the US educational psychology was dominated by the cognitive theory of learning developed by a Swiss psychologist, Jean Piaget, especially his theory of cognitive stages of development. So according to Piaget, or to be more precise, according to the US appropriation of Piaget, yes, there are four, yeah, that's a good, I see what you mean, yes, the appropriation. There are 4 stages of cognitive development at which children acquire different cognitive skills. So, for example, children acquire the capacity for logical reasoning at the operational stage, but they are capable of symbolic thought at an earlier stage. But based on his ethnographic work, Easley came to argue that there are more of these stages, and in fact he didn't even like the term stage. He used the term cognitive structure, and we have already heard about cognitive structures yesterday a little bit in Amira's talk. So Easley explained that the misunderstanding between math teachers and students happens when the cognitive structures clash. So what was the solution that he proposed? He suggested a new philosophy of teaching, a new philosophy of education. Teachers, he argued, needed to be taught how to have a dialogue with students, the kind of dialogue that doesn't stifle students' thinking. And here he is referring to this type of teaching as teaching by listening, listening to erroneous explanations, offering counterexamples to students, but generally having a dialogue that allows a student to explain why they solve a certain problem in a certain way. That is, of course, a very idealist vision of education, and Easley admits that this kind of teaching would put a lot of demand on teachers. But what's important for me, a historian of computing, in Jack Easley's shift from quantitative behavioral research to the ethnography of learning, is that he, with this career shift, he kind of supports some of the arguments made by historians of media and quantification. And those historians have made arguments about the short-sightedness of quantified approaches to societies and human subjectivity. And Jack Easley is one of the few historical actors whose career trajectory makes visible where exactly the projects of automation and quantification fall short. So that was an effort to create a system, a computer system that would cultivate free thinkers in the mid-20th century United States. In the Soviet Union, a politically and ideologically opposed country, the same interest in pedagogical computing existed. And one of the key figures in Soviet pedagogical computing was psychologist Lev Landa. What I know about Lev Landa suggests that he did care about freedom quite a lot. He himself was a Holocaust survivor, but also his son Boris belonged to the Soviet dissident movement, that movement described by Ben Nathans in the book that I showed in the introduction to this talk. In fact, Boris was one of the founders of the Moscow branch of Amnesty International, and because of his dissident activity, he he fled to the United States in 1975. I'm not going to talk about Boris today, but this is just some of Lev Lande's biographical background that I think suggests that the question of freedom stood quite acute for him. I'm going to talk about Lev Lande's research on pedagogical computing. His work happened under the aegis of the Soviet Council on Cybernetics. As was extensively documented by historians, cybernetics was a mid-century intellectual interdisciplinary movement that approached human thinking and machine behavior as guided by the same communication and control processes. And as we know from the work of Slava Girovich, in the Soviet Union, the Council on Cybernetics offered centralized institutional and intellectual support for all Soviet civilian research in computing and automation. The Council was divided into multiple sections, each of which was responsible for the introduction of computing, automation, and quantitative methods of research to a particular discipline, including psychology, biology, linguistics, philosophy, and so on. At the Council, Lande worked at the section of psychology, where he headed research in pedagogical computing. And it's important to note that he referred to his work in pedagogical computing as algorithmization in learning and instruction. And here is an English translation of one of his key monographs. So unlike Easley, Lande wasn't interested in how to teach specific subjects, such as mathematics. He wasn't involved in software development. He was interested in finding general algorithms of thinking and learning. And here is a quote that illustrates well how he understood learning and thinking. To teach students to think, one must imagine the process of thinking as the work of some device or mechanism consisting of certain components, knowledge and operations, which are connected with one another in a certain way and which function in a certain manner. So Lande was interested in operations. He sought to develop algorithms of optimal thinking for Soviet students. His definition of an algorithm came from the work of mathematician Alexander Lyapunov. By algorithm is usually meant a precise, generally comprehensible prescription for carrying out a defined, in each particular case, sequence of elementary operations in order to solve any problem belonging to a certain class or type. Applying this definition to pedagogy, Lande suggested that students should be taught with prescriptions that would walk them in small, incremental steps toward a problem's solution. In his experimental studies, and he was an experimental psychologist, and here are some of the excerpts from those studies, Lande explained that the majority of people are limited in their ability to think rationally and efficiently. Most people, when they learn new material or solve problems, undertake many unnecessary mental operations. Their mental paths to solutions or knowledge are not optimal. So Lande's algorithms were supposed to help the mind make up for these cognitive deficiencies by streamlining and automating cognitive work. To ensure that his algorithms offered the most rational mental paths to problem solutions, Lande drew on information theory to calculate how a learner could get a maximum amount of information while performing the minimum possible number of mental operations. For example, Lande used a logarithmic formula measuring entropy developed by US mathematician Claude Shannon in order to calculate an algorithm for solving a middle school problem in Russian grammar. So here is this algorithm. I'm not going to explain that Russian grammar problem here. It would take too much time. The point of this material is that Lande wrote his algorithms in verbal form and also as logic diagrams, which once again speaks to the mathematical underpinning of his pedagogical work. But in 1960s, Landa gets interested in creative thinking. What counts as a creative problem? He was drawing on the whole body of scholarship on creative thinking conducted by Soviet psychologists. But I will just briefly say that Landa and his colleagues defined creative problems as the kinds of problems that cannot be fully formalized. So let's take a look at this quote. It follows that creativity is impossible without independence and self-organization, and that creativity is creative because it does not occur in accordance with rigorous instructions, which completely and unambiguously determine actions, but rather on the basis of self-organization. So it's not only Landa's biographical details that make me say that he cared about the notions of freedom. He also mentions independence, right, in this particular passage. Okay, but then here is a conundrum. How do you create an algorithm for something that cannot be fully formalized and something that cannot be fully controlled? To answer this question, Landa turned to a slightly different kinds of algorithms called heuristics. The Greek word heuristics means serving to discover. It's a navigational term for charting one's path, knowing how and where to go. Heuristics are algorithms used in artificial intelligence research. In the logic theory machine by Simon and Newell, which I mentioned in the first part of this talk, heuristics helped a computer program solve a mathematical proof by supplying the computer with shortcuts towards the solution of a problem. To simplify, suppose you need to solve a maze puzzle. A simple algorithm would tell you exactly where you need to go, but that algorithm would be applicable to one particular maze. You won't be able to apply that algorithm to find your way out of different kinds of mazes. So in situations like this one, heuristics come handy. They won't tell you the exact way out, but they will give you clues to help you limit the number of your turns and eventually escape any kind of maze. So Landa turned to heuristics to find a way to teach students to chart their own path in solving a problem. And here is one example of his heuristic prescription to perform a geometry proof. And by the way, in his work he wrote that geometry provides more examples of truly creative problems rather than Russian grammar. So I'm not going to read out this prescription. The point is that his heuristic prescriptions, those that should have guided students to the solution of creative problems, existed only in verbal format. Because for Landa, full formalization was antagonistic to creativity. So just like Jack Easley at the University of Illinois, Lev Landa sought to produce algorithmic systems that would teach students how to think. And like Easley, he came to recognize the limitations of algorithmic systems. They are bound to control, allowing little room for free reasoning. And I think now it's time for the conclusion. What I presented today is I presented a story about computer technology and algorithms that were designed to discipline human thinking and learning. I suggested that the Plato computer and Landa's algorithms of learning were behavioral technologies. In my study of these behavioral technologies, I look at the intersections of the histories of computing, quantification, and human sciences. And I see this intersection as something worth continuing exploring. Yesterday, we talked about how mathematics is everywhere. The material that I presented today speaks to this point. Historians Ian Hacking and Theodore Porter have long demonstrated the centrality of mathematical apparatus in the making of human subjects since the 17th century. I suggest that our digital era makes the exploration of the mathematical underpinnings of present-day data-based behavioral technologies even more important. The questions of freedom and control stood acute in the mid-century Soviet Union and the United States. The questions of to what extent individuals need to be free from the state, or to what extent the state needs to constrain individual freedom, were quite acute both in the USSR and in the Soviet Union. In his 1971 monograph, Beyond Freedom and Dignity, American behavioral psychologist B.F. Skinner argued that the ideals of individual freedom and autonomy lead to social problems. Freedom needs to be constrained, Skinner argued. In the Soviet context, the whole dissident movement emerged as an effort to establish liberty in an unfree system. And presently, the questions of freedom and control remain to be acute, especially with the rise of data and algorithmic technology. So I'd like to end with questions. Do this technology inevitably discipline and control? Can they allow for freedom? Are efforts to create algorithmic technology that allow for the freedom of thinking a hopeless cause? Thank you.
Thank you very much for your really interesting talk and for being so, for being so punctual. And so we have 13 more, or 15 minutes, let's say, so for questions and answers. So are there any questions, please?
Yeah, thank you very much for this very rich talk. I wonder if there was also discussions about the social dimensions of learning mathematics, because it seems that the tension is between the algorithms and the cognitive properties of individuals.
Yes, thank you. This is such a great question, and it's really interesting to see how the social dimensions are approached differently in the US and the Soviet context. So I mentioned that, so Easley was really interested in the social tension, right? He really saw the mathematics classroom as, this kind of very interesting social dynamic. For example, some of his ethnographic studies pointed to the fact that the conformity, women are much more likely to be conformists, right? Especially young women. And what he meant by a conformist, he was saying that sometimes, elementary school girls want to please a teacher, so they want to give the right answer because they're trying to anticipate what kind of answer a teacher wants to hear, and they want to give that answer to please the teacher, right, and to appear likable, which, for example, Easley was saying, rarely happens with boys. So yes, he was paying a lot of attention to the social context. But the question is whether that kind of attention to mathematical education as a social process, right, and as a complicated social dynamic interfered with his work on the Plato. So he spent working on the Plato, I would say, just maybe 10 years, and after he leaves the Coordinated Sciences Laboratory, which hosted the Plato project, Easley writes a lot about how education is always a social process, and especially he views mathematical education as a social process. So I actually view his exploration of the social aspects of mathematical education as an implicit critique of the Plato project, which is kind of which is not cognizant of those social underpinnings of learning. It's really interesting that I haven't found any references to the social aspect of learning in Lev Landa's work at all. Thank you for the question.
Another question, please, Ursula.
Yeah, that's a wonderful talk. I wanted to steal a whole lot of your slides and stick them in my talk, but since in an hour's time, I can't do that. One of the places I've seen is these attempts at trying to teach people formal proof analysed is in the whole movement in computer science that thought that the education of computer science needed to be about teaching people to prove programs correct. I think it was more of a movement in the UK than, well, certainly a movement in the UK. I don't know about in other countries, but there were quite, well, I think I do want to use the word naive, or quite amusing attempts, you know, to sit a bunch of programmers down, or a bunch of programming students down in front of a sort of 20 years later version of that Plato thing, and you know, and then just assume they would learn how to prove things. But then, because of a slightly different context, they then weren't afraid of expressing their frustration and how silly they thought this was. And there was then quite a dynamic debate in the computer science community about the cruelty of teaching programming, i.e. the cruelty of teaching programming that way. It's a very interesting parallel to draw.
Yeah, I'll respond to this. Thank you so much, Ursula. I really look forward to talking more about the teaching of the programming and the cruelty of the teaching of the programming. Especially, it's interesting that you're mentioning it because we are also familiar with the efforts to teach programming as a way to teach. Also, you know, creative, free-thinking dispositions, and I'm thinking about the Logo project, right, at MIT. I do notice that same kind of, you know, cruelty, at least in my opinion, in that Plato proof course, right? I said it looks extremely bizarre, and I do believe that this program was teaching students to do proofs like a computer, which is probably, you know, when you make people do something like a computer, I think it is cruel, right? And I'm thinking about, you know, this human, this kind of assemblages, right, of humans and algorithmic systems now, where human labor is not replaced, but it is regimented by computer systems, AI systems, and there is so much cruelty in it. And I agree that in the pedagogical projects that teach people to think like machines, there is also some implicit cruelty.
Yeah, thank you. I really enjoyed your talk. It's very interesting. And I think it also has a lot of, today, the same kind of things are going on, right? So I just have, two questions. So the first one, you said that the idea with Plato was to replace human instruction. So was that in all subjects, or were they mostly thinking about mathematics? So that's the first one. And the other one is, it was also about, if I understood you correctly, the idea was that they wanted to teach students how to think, discovery way of thinking. So, and that example you gave from the Plato. So I was just wondering, so how did they, were there discussions about how this discovery part was kind of implemented? Because it was very difficult, as you also said, to see that. And also, if I understood you correctly, that's also why Jack easily, at the end, became very disappointed with the whole thing, right?
Yeah. Thank you so much for these questions. So the first question was about the subjects. Was it just mathematics or other disciplines? You know, virtually every subject, they created a lot of courses for obviously language classes, biology, genetics, chemistry, you name it. And easily was actually involved in developing all this other discovery courseware for the Plato computer in all these other subjects. For example, there was one course on chemistry where students could actually, in a virtual laboratory, experiment with chemical substances. And I found a lot of students' evaluations of those courses, and students were furious because they couldn't understand what they needed to discover. So it was extremely confusing. Okay, so, but what what did ease the, and oh, by the way, another thing that I wanted to say that in the courses, the discovery courses in mathematics were, no, there were not so many of them compared to, for example, natural sciences. The development of the courses in natural sciences was actually, so some of those courses were appropriated by University of Illinois researchers to use those courses not as to teach students, but to use them for their own research. So here is what I mean. Well, forget about mathematics for now, but if you create a computer-based course in, say, economics, you need to collect a lot of knowledge, right? A lot of data, and you basically create a data bank, and you develop operations how to work with the data. So later you can use these lessons for your own research. And one of the economics professors at the University of Illinois used the class that was developed to teach population dynamics, but he used that software to create his own models of population dynamics in his own research. So when it comes to mathematics, this proof course didn't have those ramifications, right, in the field of computing. Okay, and now your question about the discovery, where exactly the discovery happened here. Okay, so that's a great question. So one thing that I suppose is that at some point students needed to identify what principle they are working with here. So they needed to, I guess the point wasn't just to finish that proof, but to learn the principle at the heart of this proof. And I think here the principle is that you can, when you do multiplication, you can actually move different numbers, and the sum doesn't change, right? Even though one of them is negative. So if you move -1 multiplied by a and add b, it's going to be the same as b plus a multiplied by a1. So I think that what the point of this was to discover the principles, not to discover how the final line of the proof should look like, but what's the mathematical principle that should be used in order to arrive to the final line.
So maybe we have a time for a short question. So if not, I think we can thank Ekaterina for her work.